first thing that you might think to say is to say, well, we've got traditional models on one end of the spectrum that are really have a lot of structure and are easy to interpret. We've got learning algorithms on the other end of the spectrum that are really flexible but difficult to interpret. So could I just put some more structure into the machine learning algorithm to get something that has enough structure to do statistics, but not so much structure that I end up screwing up the part that's giving me good predictions? And the short answer to that is really not so much. There seems to sort of always be this level that once you cross it in machine learning, you're essentially just back into the context of doing traditional statistics. Okay. And another problem that we're going to have is that when we do things with bootstrapping, that typically means that everything is really, really correlated. And that's not a framework that we typically want to work in as statisticians. And so the idea here is that, first of all, instead of doing bootstrapping, we'll do subsampling. Okay. That's sort of the first obvious idea. But the more important idea is that instead of putting the structure that we need to do statistical inference, instead of enforcing that structure on the learning algorithms themselves, we'll do something like the ensemble methods, like bag trees and random forest that I talked about, and we'll put the structure on the data going into the ensemble instead of on the learning algorithms themselves. Okay? Questions so far? Okay, so we'll see in a second that the final version of the estimator that we want looks a lot like a use statistic. So most of you probably haven't seen use statistics, but this is a very brief but also very, very classic introduction to use statistics. So suppose that I have a sample of size n that are independent, identically distributed from some common distribution. And suppose that I have some estimator or some parameter theta that I want to estimate. And now say that I have some estimator h of theta that I know is a good unbiased estimator, but it only requires k arguments, where k is less than n. So I've got a sample of size n, but I only need a sample of size k to get a good estimate. So you can think of saying, well, I could take first k arguments in the sample, I could take random selection of k arguments from the sample. Not so surprisingly, the best thing to do is typically to take all subsamples of size k from your original sample, evaluate the estimator at each one, and then average over all of them. And when you do that, this resulting statistic, U, is called a U statistic. So the fact that you could average over a bunch of good unbiased estimators to get another good unbiased estimator is not something that's all that surprising in statistics. What's more surprising and will end up being a lot more helpful for us is that these things are still asymptotically normal. So there's a central limit theorem that goes along with U statistics that's actually a lot stronger than the classic central limit theorem that probably most of you have heard of. So the classic central limit theorem says that, again, given the same sort of situation where I have a sample of size n, that everything's independent and identically distributed, if I take that average, then that sample average is normally distributed. But here what I'm saying is I don't actually have to average over the data itself, but I can actually average over functions of that data. And the important thing about this is that even though we assume that that original data is independent, these functions of the data are explicitly dependent. Right? There's going to be overlaps between those subsamples, which means there's going to be correlation and dependence between those functions, between those estimates. But when we do that, we still get something that's asymptotically normal. So in this context of U statistics, this unbiased estimator H, this is what we call the kernel, and then the size, the number of arguments that that kernel takes is called the rank. So this is a U statistic with kernel H of rank k. So this is, I won't get into this today, but this is just just think about the variance parameter. I'll talk about it a little bit in a couple of slides.
So it's sort of like a variance and a random variance variable?
It's a variance parameter, so it's not random in the sense that it's something that we need to estimate. So it's a property of the limiting distribution. I'll talk about it more in a couple of slides.
What's the upper limit in the summation?
So this is just over, it's summing over all subsamples of size k.
And choose k up.
Yeah. Okay. So at this point you might say, okay, well, given this result, we could stop here. So we can view our original training set as the initial IID sample, right? And then we take all n choose k subsamples of size k from the training set, and with each one of those subsamples we build a tree, and then when we want to make our final prediction, we predict using each one of those trees, we average over all of the results, and this is what our final estimator looks like. And that's a U statistic, right? So in this context, this tree that predicts at x star, that's the kernel, and then the size of the subsample that we put into each tree, that we build each tree with, that's the rank of the subsample. Right? So there are two fairly obvious problems with this, or I guess one more obvious than the other. The first sort of obvious problem is that computationally n choose k is an awful lot of things to deal with. Right? We really don't want to have to build n choose k trees every time. We want to build m trees, which is less than n choose k, and then average over these. And so this is what that final estimator would look like in this context. Now, when you do this, in theory, this is just called an incomplete use statistic. And so there's been at least as much theory devoted to incomplete use statistics as there has been complete versions of use statistics, where we take all n choose k things. Because this is not a problem that's, all that subtle, right? When you use these, you typically don't want to have to do all n choose k of them. So if this was the only problem, we would still mostly be okay. Where we start to get into problems is where we say, what we really want to do is to let k grow as n goes to infinity. Okay, so in our context, k is the number of subsamples that we're going to use to build each tree with. Okay, so the more subsamples we can put into each tree, the deeper we can grow the trees. So the more constants we can have in our piecewise constant estimate, the better the approximation is going to be for each tree, the better the overall average is going to be. So the larger k is, the deeper we can grow the trees, presumably the more accurate our predictions are going to be. So we want to let k grow as n goes to infinity. So now we have something, it looks like about the same thing, but now we have this extra subscript on the k to make it explicit that we want k to grow with that. Okay? So this is where things start to get a little bit more complicated. So in this case, in the case of bagging, which we'll talk about again in just a second, we call these infinite order use statistics. And in the context of random forest, where we're putting that extra omega in to add a bit of randomness into the model, we call these random kernel use statistics. Okay. So this is sort of the first big result. This is a central limit theorem for use statistics when k is growing to infinity. So not taking into account the extra randomness, but this covers the case of bagging, which I talked about at the beginning. So where we just take bootstrap samples, build a bunch of trees. Each tree is built in the same way. And I won't go through all these conditions in detail, but what's important to point out here is that essentially what we're saying is that no matter what we do, we always end up with something that's asymptotically normal. Okay? And the only thing that's changing here is the asymptotic variance, which is in the denominators of all these. And more so, this asymptotic variance only depends on the ratio of the size of the original sample to the number of trees in the ensemble. Okay? So in every case, we get something that's asymptotically normal. The only thing that's changing is the limiting variance, but we know how to estimate that. I'll talk about that in just a moment. Okay. Again, this was just in the case of bagging, where we assume that everything's grown in the exact same way. When we get into random forests, essentially what we're saying now is that those limiting distributions that we got in the case of bagging end up being the same as in the case of random forests, subject to this additional condition here, which may not look all that nice, but actually what this is saying is that whatever we're doing to the trees to try and help them find those smaller patterns, whatever that omega is doing, it just can't be pulling predictions further and further away as n goes to infinity. Okay. And in fact, in practice, this limit usually goes to 0. So the fact that the only restriction is that it can't go to infinity is actually a pretty weak condition. Okay. All right. So the takeaway from those two theorems is that whether we do bagging or random forests, we're going to end up with something that's asymptotically normal. And moreover, we know what closed form for that limiting distribution. We know what the parameters look like. And those variance parameters only depend on the size of the original ensemble, or sorry, the size of the original sample relative to the number of trees in the ensemble. Okay, so the number of data points that we originally had relative to the number of trees that we're going to build. Okay. And I'm not going to get into how we estimate the variance here, other than to say we can estimate those variance parameters, and we have sort of two methods for doing this, which we call an internal method and an external method. So the external method is what you might sort of typically think of. We build the ensemble, we use the same data to estimate the variance parameters, and everything works out all well and good. But what we show in the paper is that by actually structuring things in a slightly different way, we can do this internal procedure where when we build the original ensemble, these variance estimates sort of pop out for free. Okay, so we're able to estimate the variance with the original data and at no additional computational cost to actually building the original ensemble. And that'll come up when I talk about intervals and a few snippets. Okay? But at this point, so we know what the limiting distributions are, we know what the parameters are, we know how to estimate the parameters in those limiting distributions. So now we can start to do statistical inference. So in particular, we can get confidence intervals by just sort of taking the appropriate cutoffs from each of those limiting distributions, and we use that as a confidence interval. So again, intuitively, what that means is that if I have some point where I want to predict X star, and I want to get some notion of how stable that estimator is, what that's really saying is that if I was to get a new data set and I redid the learning algorithm, or I rebuilt the ensemble, and then I predicted X star again, how different might I expect those predictions to be? Okay. Questions up to here? All right, so that was confidence intervals. So now we'll talk a little bit about hypothesis testing. So this is the same setup that I had shown you before with these hypothesis tests for feature significance. Before I called these X1 and X2, now I'm going to call them XR and XA. So again, these are just sets of those features. Okay, they could be single features, one feature XR, one feature we call XA. Or we can think more generally of them just being some subsets of the features. So XR stands for what we can call a reduced set of features. So they're features that we either know are important or at least that we want to keep in the model. And then XA we'll denote by all of the additional features that we want to test to see if they are actually important. Okay, so now our null hypothesis looks something like this. Can I write this relationship F as just a function of those features that are in XR? And the way that we think about doing this is to say, okay, well, I'll build one ensemble using all of the features, right? Using everything X1 through XP, or put another way, using both XR and XA. And then I'll build another ensemble where I only use the features that are in XR, so where I don't make any use of those additional features whatsoever. Now the nice thing about doing this is that a couple lines of algebra